Good morning. For this last days of our conference. Today we have Luca Lionni from Universität Heidelberg, who's going to talk about tensor invariants and entanglement. Please.
Thank you, Jaime and Johannes, for inviting me. So I haven't been working on a non-perturbative QFT recently, so I chose to rather present some other point of view on the objects and distribution of that appear in studying random tensors. So first I'm gonna redefine a bit what I mean by tensors and how they appear in quantum physics. Go backwards, then tell you about unitary matrices and tensor invariants, and about some kind of unitary invariant tensor distribution and how it appears in physics. So this is more introducing some notions and so on. And then I'm gonna, to perform computation in a limit of infinite n, I need to introduce some ensemble of density matrix. So I'm going to do that and explain what it means in quantum physics, and then present some results. Let's see if I have time. Okay, so what I mean by tensors here is some arrays of number, but with d inputs and d outputs. They are labeled, they don't have symmetries, they're labeled by an integer on each side that is called the color. And so you could represent them by some box with the inputs and the outputs. And if you have a matrix, you just have one input and one output. And as you know, summing indices is represented by an edge between an input and an output. So why this definition as matrices with subdivided indices? It comes from the fact that in a quantum system, if it is formed of a number of subsystems, then both density matrices and observable are operators on a tensor product. And then with some choice of basis, they're represented by such complex tensors. So you have other properties, like being Hermitian, and then different for states or operators, but okay. And so the size of the index set of the tensor is the dimension of the subsystems, which you could take to be different, but I'm usually going to take it to be the same. Okay, now that this has been said, you could decide, for instance, to consider tensor for which the outputs and inputs are split, meaning it is where is it? A tensor product like this. And this is, okay, closer to the tensors you have seen and that we study in, should I click on something? And that we study in random tensor models. And in quantum physics, this means like that the state is pure, so no connection between the outputs and the inputs. And you could also, yeah, that was easy. You could also have mixed states, meaning not pure, so you have connections between the entries and so on. And an example of a mixed state is the identity matrix, which is actually, if normalized, maximally mixed. Okay, so other properties of tensor, you could split it in another way. Instead of splitting the inputs and the outputs, you could split subsystem by subsystem, so color by color, then you have a tensor product of matrices. So that would be like a factorized state, but if you are looking at an observable, it means it is local. It acts independently on each subsystem. And what one thing that we were interested in when studying such quantum system is entanglement. The definition is that it is an entangled density matrix is one that you cannot write as a convex combination of factorized states. Okay, but this is the formal definition. I'm not going to use in this form. But okay, entanglement is important both in quantum technologies, but also in, for instance, the study of black holes or holography and so on. And when we say bipartite state, we mean that you have two colors, and multipartite means more colors. Okay. Okay, so now that I've introduced this, some questions that are important from this context are, if someone gives you an unknown tensors, how many operations can you do on it to reconstruct it fully? So that would be a lot. And that would be too much. You don't need all that information for the applications. So another a priori less difficult, less expensive problem would be, can you recover theoretically or experimentally some information needed to characterize the amount of entanglement between the different subsystems? Okay, but that is difficult also, very difficult. And I'm going to go on and I'm going to add some points here on things that are important to ask about a tensor from this context.
So for matrices, you cannot have entanglement.
Well, looking at like a matrix is like looking at it without worrying about the substructure of your system in a way. It's just it's not that you don't have entanglement. It's like you decide not to study it. So so things that yeah, exactly. Okay. So another notion that appears in the study of entanglement and that I'm going to talk about rather than this other notion I introduced is related to local unitary matrices. So what I call local unitaries, anything local unitary is a tensor product of unitary matrices, one per subsystem. And so LU always refers to that. Local unitary transformation is the conjugation by such a tensor product. Graphically, it's something like that. And okay. LU equivalence for two density matrices is the fact that you can obtain one by conjugating the other in such a way. Local unitary invariance for a function or a distribution is that it is invariant under such transformations. And so local unitary invariant homogeneous polynomials and so on are some polynomials. Okay, this is things that have been said already probably, but the homogeneous polynomials that present this invariant you can characterize as the ones for which index summation respect the coloring. Okay, so these are some examples. Okay, and so these invariants are the same thing as the tensor invariants, and you can see it easily on the graph by just like, in the pure case, you flatten the two tensor in two vertices, and because of the coloring, you could go back. And here, if you have a mixed state, by flattening, you have to remember the presence of that box, so you have an additional color. And okay, so okay. So why do we care about local unitaries? We care because, so there's a theoretical notion of entanglement, and two density matrices have the same theoretical entanglement properties if they are local unitary equivalent. So if you can obtain one from another in this way. And so I'm saying theoretical because there are some more applied notions of entanglement that are more practical in performing computations, for instance, like quantum operations and so on. But so this discriminates too much. So it means two density matrices in the same LU entanglement class have the same operational entanglement, but the converse is not true. But in any case, so one thing that people do in quantum information is that trying to find entanglement measures, so functions from density matrix to real numbers, for instance, which would give the same value for density matrices that have same entanglement properties, but would give different values if they have different entanglement properties. And so because of what I said, all of these functions should be invariant under local unitary transformation. And in the same way, in the same way, local unitary invariant distributions, which I'm coming closer to random tensor models, local unitary invariant distribution, they average over some properties of your density matrix that don't matter when studying entanglement. And so they allow studying typical properties of these theoretical entanglement classes. And there's a big use of random tensors in random quantum state in this context, for instance, in the work by Page and so on. Okay, so some example of such invariant distribution, the tensor models that so part of the audience studies appear in this context. And for instance, if you normalize them, they provide such distributions of quantum states, pure states here. And the Gaussian one, so if you don't have an interaction, it is often used in both more applied quantum physics computation, but also like this literature on black hole evaporation. So it's the same thing as having a big R unitary matrix acting on a fixed state. And so the initial computation of Page curve, for instance, is performed with a state of the kind. Another kind of distribution of the form is you fix a density matrix. So you fix a tensor, and then you conjugate it by a tensor product of unitary matrices that are independently distributed according to the R measure. And so here you're really averaging, you're fixing a density matrix and you're taking a uniform, in a way, uniform density matrix, a random one, inside this entanglement class. And so this is a random tensor, but then you're interested in measuring, so you can define like this quantity, for instance, which is the average of the observable O on the random state inside this entanglement class. So it's going to tell you you can choose O in the way you want, and it allows you probing the properties of this entanglement class. Okay, now coming back to invariance. So why do we care about these polynomials? Well, apart from them being correlations and interactions of random tensor models, well, they separate these entanglement classes. And in this way, they contain all the information on the entanglement class. So if you have a finite n, there is a number that depends on n. If you know all the first invariants, you're going to know exactly in which class your density matrix or tensor is. And furthermore, we're still in the process of clarifying a bit this, but these invariants, it's also a free family. So they provide a basis for you. So in a way, what it means is if you have a quantity that is local unitary invariant, like an entanglement measure or something like that, and you happen to have an expansion on such polynomials, for instance, because I'm going to be interested in this limit, in the limit of infinite size, if you have an expansion or series expansion, then it's unique. The coefficients are unique. Okay, and okay, so it's one approach, one philosophy in studying LU invariant functions or distribution is to expand things on these bubbles, these polynomials, these tensor invariants. And I'm going to present some results in this way. Okay, but just to say, these invariants, they also appear generally in the study of multipartite entanglement. For instance, more recently in holography. And so I promised I would add things to the list. Here it comes. So you have this more difficult question. One question you can add is, given an unknown tensor, can I identify the theoretical entanglement class? So it's going to be somewhere in the middle. It's less information than reconstructing it all. But it's more than the information you need for the operational entanglement. And so from what I said before, it's like having a certain number of the local unitary invariants, these tensor invariants. And if you're in the limit of infinite size, you need to know all of them. So it's still a lot to do. But it's also things that we have been computing for random tensors, for instance. And so you could add something instead of really identifying the theoretical entanglement class. You can say, well, I'm going to choose my favorite one, and I'm going to see just this invariant, what information it contains on the entanglement properties, or more generally on the tensor. And so this is what has been done a lot, actually, because one particular case of this is studying Renyi entropies in quantum physics. So I'm going to detail what that means. Okay, Renyi entropies are the following quantities. So rho I is, you choose a set I of colors, and you partially trace the ray. Partially tracing is doing something like that, or on the colored graph is having the edge parallel to your density matrix. And taking a trace of n copies of that, so you put n copies, and then all the remaining color you put in a parallel way. So these objects, they're depending on the number of colors that remains, we call cyclic melonic or necklaces in tensors, in random tensors. And so they tell you how mixed, they get the information on how mixed these rho i's are. So how much of the tensor is located in between the inputs and the outputs, basically. And but by combining information on how mixed these different things, how you get information on the entanglement detail. But then you could look at other tensor invariants. For instance, you can look at this K-free graph, or if you suppress the density matrix for pure. So it's something like that. So in the quantum physics context, they're called moments of the partial transpose, and they contain more information. They actually contain fine information on the entanglement. So knowing one of them gives you good information, and knowing all the family gives you a lot of information. And but you could also decide to study other ones. For instance, this thing. So this we've studied in random tensor models because it counts gluings of octahedra, for instance, in the three-dimensional perspective. And so it's been studied recently in a holography context to study entanglement properties. And okay, so this was to illustrate this. Like you could try to know all of them. That's a lot, and that's too much. But you can also choose some of them, and choosing your favorite one is a relevant problem potentially. Okay. Now, focusing on one of the unitary invariant distribution I mentioned, which is called randomized measurement. So I repeat what it was. It's like you take a tensor product of unitary matrices that are independently are distributed, and you take something, your an observable of your choice, a tensor of your choice, and you take this trace. So this is a real random variable. So to interpret this, you could see this in two equivalent ways. You can see this as observing your observable A on the random state in the entanglement class. So this I already said. But you can also see it as fixing a row and taking an observable and randomly rotated it locally, and then applying this to measure your system. And the reason I'm saying that is because this can be done experimentally. So you can simulate local rotation. I mean, you can create local rotation, you can apply them to your observable, and then you can apply it to density matrix. And in both these cases, the philosophy is you have it's a probe. There are good or less or good choices, and you try to extract information on your tensor using this. And this is, I told you before, because it's an example of a LU invariant distribution. Okay, so I add something to the list. I put it a bit on top. This is everything I told you before. I can add something, like you could say, okay, another problem is I have an unknown tensor. I study this random variable. What information do I recover on this state? And this is what is called randomized measurement. And so I'm recovering, with respect to that, some of the information about the LU invariant, the LU entanglement class. And typically, because I can express this as sum over tensor invariant, what you get are, at least in the limit of large n, you get information on dominant, like the strongest one in n. And this is interesting for our purpose because it's also the kind of questions we have in random tensor model. And okay, one question I had here, because that's what I want to discuss at the end if I have time, is, okay, so the observable is a probe that you use and you can choose any one you want. So are there better choices than others? Okay, and so more on this thing, it's called local randomized measurement. So there's a full literature on that from the last maybe 5-7 years, something like that. And what people do is they take small systems like bipartite, three-partite, something like that, with qubits, 3 bits, something like that, and they compute things and they do experiments. And so they found out that so it's good for many things. You can do many things with that in more efficient manner sometimes than you would do otherwise. Like if you have really like you're trying to do quantum computers, you have some quantum algorithms, they produce for you some density matrices. You want to be sure it produces the same thing, for instance, so you have to compare the outcome. And sometimes the outcome, these have been performed in different places. And so you can use that to compare them, or you can use that to measure like form factors or out of time order correlators in many body systems to measure chaos or thermalization and identify topological phases and so on. Okay, solve some experimental issues. So I'm just explaining why there's a literature around that, people like that. And also, which I find amazing, is that everything that they publish theoretically, they verify experimentally. So connects a bit to the real world. Okay, but so what we're doing is a bit further away from the real world, but still is we take really this problem for D general, but take the limit where the local dimension of the subsystem goes to infinity. Because here you can hope to solve things exactly, actually, and it's very similar to things we do in random tensor models. And so how do you study this? This is a real random variable. So one way to study it is by computing its moments. The moments are integrals over unitary matrices that look like that. And you can also directly try to study the generating function of moment, which is a generalization of HCIZ integral. For the HCIZ integral, it's D equals 1, and you just have unitary matrices. But here now you have, yeah. Sorry, it's Harish-Chandra, it's Zuber. And I mean, initially it's more Harish-Chandra, but it's been popularized in physics by Zuber. And it appears everywhere. So the integral for D equals 1 is very well known. It appears everywhere. Okay, and to connect with non-perturbative QFT, one relevant question in this case is what are the analyticity properties of such integrals and general unitary integrals, like also Resemble-Witten integral and things like that. And this has been studied by these people. And for the generalization to tensors, I don't know. It's a relevant problem. Well, okay, so we're going to study this limit, and as I said, we will do that in the limit when the local dimension goes to infinity. Well, in this case, it's more efficient not to study the moment, but rather to study cumulants, connected correlations, which are the coefficient of the expansion of the logarithm. And so we have a general result for that, which is in the form I motivated before. I said, we're going to have LU invariant quantities and so on, because the tensor invariants provide a form of basis. We're going to expand quantities over these invariants. So this is done here. It's locally invariant both for transformation on A and rho. So it's a double expansion on tensor invariants in A and rho with some coefficients. And so this is a sum of our colored graph for both A and rho that are not necessarily connected. It's a 1/n expansion where we know the smallest integer, but I didn't write the formula, and the coefficients here, they're combinatorial numbers, so they're numbers expressed in terms of counting permutations and so on, and they are generalization of Hurwitz numbers. And just like Hurwitz number count ramified coverings of the two spheres and so on, these counts ramified covering of nodal surfaces. Yeah.
So this is, so you mentioned Jonathan Novak on the previous slide. He has also worked recently on large N of this Hallstatter-Christensen-Zuber formula. Is your formula now a generalization of his formula? If you put D equals to 1, do you get this formula back?
Yeah, absolutely. Yeah.
Okay.
But we don't have the analytic.
Okay. Yeah.
Okay, so this is okay, and then the goal from this is to take a large N limit. But first, I add the slide, and then it's exactly what I just wrote. So we want to take a large N limit, but these things, they depend on the dimension, and so. So here you have different approaches. Either you have a concrete example that is, it's interesting, so you want to compute it, so you plug it in and so on. Or here what we do is we make an assumption on the way these scale with the dimension, and we perform computations this way. And so the assumption we do is the following. So we suppose that the invariants of the density matrix have a dominant term where with some power of n that call scaling, whatever, something that doesn't depend on n and some subleading terms. And then we make a specific assumption for this exponent. We suppose it interpolates between the exponent of the identity, which is not untangled and maximally mixed, and the exponent of something called HCIZ state, which is very or maximally untangled and pure. And the HCIZ state is something like that. So it's in like physics, like quantum physics notation, it looks like that, but in tensor notation, it's like that. So you sum over J, if you have components like this, you sum over J, and you have delta functions that identify J to all the indices.
Yeah, Z is Albert.
Hmm?
Yeah, Z is Albert.
Probably. Yeah. I usually just refer myself to Wikipedia. Okay. But okay, it's the reason why we choose this is because it's a state that is very studied in this situation. So I'm going to tell you a bit what it means to do that. But just to say, these scalings here that I put like that, you know them exactly. The scaling for the identity. So you have a color graph. The scaling for the identity, it depends just on the number of faces. So bicolored cycle that have some color C and the A, like the tensor. And the ones for HCIZ is just the number of connected components of the graph if you remove the A's. So here it's 1, but it could be something else. And you can also change this state, for instance. So we also did a computation with a state which mimics more, instead of this, the bicolored, like the faces of tensors. But the results that I'm going to present are the same up to something. Okay, so just to say again, we're going to compute the expansion on these tensor invariants for the connected correlation of the distribution of this real random variable. And we're going to do so in the limit of infinite n for rho like this. So we did an assumption for this. And for A, we suppose that the observable is local. That is, it is made of, it's a tensor product of observable applied independently on each subsystem.
Beta and epsilon, something you've determined but not writing down, are they free functions?
What?
The coefficients, beta of rho and epsilon of rho,
yeah,
are they definite functions you've just not written down?
They're parameters. I assume that here I assume that rho is such that there exists beta and epsilon such that the scaling writes like that. But now I'm going to tell you how to interpret these parameters. So before the precise meaning of epsilon and beta, I just want to say what is the meaning of just the exponent itself. So the interpretation comes from defining entropy, so generalized entropy, so which are just basically minus the logarithm of these invariants. So if you do that, then you have a dominant term, at least. So if the scaling is non-zero, this is the part that will dominate for n sufficiently large. And so in first approximation, these entropies are given by this term, so by the scale. Of course, this holds if n is sufficiently large. And okay. And okay, that I said also. All right. So I define this for any invariant, but there are some invariants that have been studied a lot, as I said before. So they're Renyi entropies. So if you fix the invariants to be these necklaces and you do that, the scaling you get is the dominant part of these Renyi entropies. So if you do that just for rho without partially tracing, the thing you get by assuming rho to be in this ensemble is beta. So the one that multiplies the identity. So for n sufficiently large, beta tells you how mixed your state is. Now you could partially trace, and then you can do the same thing, and then epsilon weighs in. But here you have a sum. But for instance, okay, so first consequence of this is that in the limit of infinite n, epsilon plus beta are in some triangle like this. And then you can compose these two, like you can sum this and this for the other ensemble, and take subtract the full Renyi entropy, and then what you get is precisely epsilon. So epsilon is the mutual information for the Renyi, and the mutual information tells you the amount of correlation between the colors in a way. So it informs you in this sense on how entangled the state is. But I'm going to make this more precise. So by using this theorem by Horodecki brothers, that says that it's called conditional inequalities. So with a condition on the size of what is traced, if the max of the two Renyi entropies is larger than the Renyi entropy where nothing is traced, then all bipartitions of your D subsystem in two groups of size I and D minus 1 I are entangled. And in particular, and this is what I will use later, if epsilon is large, so I said it relates to entanglement, if epsilon is sufficiently large, more precisely if it's larger than beta D minus 1, then you know that from this that all bipartitions of the subsystems are entangled. And there's a name for that, it's called genuinely entangled. Okay, now that I introduced all of this, I'm going to present you some results. I don't know how long. Great. Was that already 5 minutes ago? Okay, good. Okay, so first, I want to present results for everything I introduced before. Okay, so first for the moments of this distribution. So the moments of distribution for rho in this ensemble and a local density matrix, you get nothing in infinite n. So you only get back something about the observable. You get no information on rho. But this, from the viewpoint of large N quantum field theories and so on, this is not very surprising. It's just like saying that your disconnected observables factorize at large N. So you just want to study connected correlations. So let's do that. And so first we suppose that the observable is has rank 1, basically. So we're assuming it's just a product of delta function that, so just the first element every time is 1 and the rest is 0. But what I hold would be true if just you assume that the rank is very small with respect to other quantities. So and you plug this here together with the other assumption. So what you get then is this diagram like that. So this is the triangle of possible epsilon and betas. And so you have a line which is epsilon equals to beta d minus 1, and you can recognize whether your density matrix is has epsilon bigger or smaller than this line. So and so we said before that. Okay, then I say again. Here, what you get is the Renyi entropy. So you get, I mean, n purity, so trace of rho to the n. So you get beta, for instance. And what you're getting is information on these cyclic Melloni graphs. And here in the bottom corner, what you get is rather, so here I'm being a bit vague, but the idea is that you get something like a sum of the invariants for some Melloni graphs, which are the ones that appear in the SYK model. So they're defined here like that, where if you locally for any box, the edges of a given color lead to a different connected component. So it's like saying it's Mellonic, but okay, no. Right. The color given by the tensors is on the Mellonic pairs for people who know. Okay, but the point is you get some other quantity, and what you get is a sort of averaging over certain tensor invariants, dominant ones, and okay. And so you can recognize because it's very different, and also you have a very different scaling, for instance, of the cumulants. So in a way, you can recognize where you are. And the states that you recognize satisfy this inequality I presented before. So you know that the states you detect are genuinely entangled. So they're yeah, sufficiently entangled, more entangled than other states, whatever. And okay, so that's good. And now, so I said before, so you have this liberty of choosing the observable and using it as a probe and so on. So in this ensemble, at least, let's try to measure a bit the influence of the choice of observable. So here it is. So instead of taking something that is of rank 1, I take something where all the AC have the same rank, and this rank is n to the alpha with alpha between 0 and 1. And I vary alpha. So if alpha equals to 0, I've already presented it. If alpha is between 0 and some critical value, some transition value, then you still detect, but what happens is that the zone you detect shifts. So the states that you detect are less and more entangled. And then passing at that value, you just detect at 1 over d minus 1, you just detect the maximally entangled ones. And when it's above, you don't detect anything. But so that tells you that in this model, it tells you that if you want to detect, you should choose observable of the lowest possible rank. But it also tells you something. It says that so you get different information in these zones. You get different information. So it says that if you combine two measurements, one with a big observable of big rank and one with an observable of very small rank, you get a combination of these two information. So for if you have two tensors, this information is the mutual information. So it tells you precisely some information about some Renyi information about the amount of entanglement. And so more than just knowing that epsilon is better than beta d minus 1. And but interestingly, for more tensors, what you get is not the mutual information. It's something else that looks like a sum of some Melloni graphs minus the Renyi entropy. And so okay, and so a little novel for you for the conclusions. First, one message is these tensor invariants that we know from correlations and interactions of random tensor model, they appear naturally in studying entanglement, where they're called local unitary invariants. And there's a growing literature on picking one invariant, for instance, and trying to understand what it means for entanglement. And Sylvain is going to talk more about random tensor networks, for instance, that are, okay. And just to say, in this holography literature, where people take these invariants and so on, it happens that the color triangulation dual to the color graph does play a role. I don't understand exactly yet how, but it has something to do with back-reacted geometry or whatever. But it's fun to know that also this part plays a role in this context. Okay, I tried to explain that when n is large, the dominant part contains some information. In particular, just the exponent already contains some information through, for instance, I illustrated with this 2-parameter family. And also, right, so what I said orally, this what you get from more tensors here, like by combining two kinds of results is like a difference between this and this, for instance. This provides new notions of multipartite information, and we have no clues what they mean. More generally, what do like Melloni graphs, or like, yeah, the notion that dominant graphs, what information do they contain on entanglement? This we don't know. And more generally, many things that we do compute for random tensors do have an interpretation in this context, including some questions about analyticity. So it was okay that I speak in this workshop. Thank you.